Thank you, Aruna. Thank you for inviting me. It's very honored to give a talk at Copenhagen-Jerusalem combinatorial seminar. Okay, today we will discuss a progress on the complexity theory of manifolds and cobordisms, which gives us a nice bound on rho-invariants. And as ingredients, we will talk about hyperbolization method and a combinatorial concept regarding polyhedra. So this is a joint work with Shmuel Weinberger. Okay, here's an outline. So first, we will take a look at Gromov's conjectures as our motivation. And as next, as a background, we will briefly take a look at some short history of Cheeger-Gromov at rho-invariants and Chang and Weinberger's topological definition of rho-invariants and Cha inequality for three manifolds. So for low dimensional manifold. And our main result is to obtain linear bound for high dimensional 4K-1 manifolds. And also we have analogous inequality for Atiyah-Singer rho-invariants. And if time allows, we can talk about some applications on the complexity theory of homotopy length spaces and further work. Okay, here is a nice picture of our universe. So let's assume that our universe has. So this one is just easy, quick motivation. So let's assume that our universe has the starting time and end time, like a Big Bang and Big Freeze. So Big Freeze is kind of that eventually all matters get cooled by the second law of thermodynamics. So, and okay, so we have the starting time and ending time of our universe. And as a mathematician, we may ask that, oh, how our universe looks like. So at this point, we don't know, but let's assume that our universe is simply connected. So for example, pi1 of our universe is just trivial. So let's assume that at this moment. And then we may want to prove this fact experimentally or quantitatively. So for example, so here is the Earth, and we are standing on the Earth. And let's assume that we have a observable, very large loop looks like that in our universe. And so mathematically, even if we know that our universe is simply connected, in order to check that fact experimentally or quantitatively, then we should shrink this big loop to a one point. So, but if the disk bounded by this observable loop is too large for us to shrink our loop in a one point by the end of the universe, and then we cannot prove that universe is simply connected experimentally. So asking the minimal area bounded by the given loop is meaningful question to us, and we may generalize this type of question to other n-dimensional spaces, the n-dimensional manifold. So, okay, so when we generalize this question to manifold M and n-dimensional manifold M, looks like this, then the first question we can ask is whether if our manifold M has a filling. So here's a quick terminology. So for example, when you have S1 is here, and we can think of two distinct copies of S1, then we say that this S1 and this space and this space are cobordant if there is one-dimensional higher manifold, looks like this, whose boundary is this top manifold and this bottom manifold, then we say that these two spaces are cobordant. And we think of more another easy examples. Then when you think of some copies of, let's think of 3 copies of S1. Then we can think of these kinds of 3 legs, looks like that. Then S1 is one manifold, and this one is a surface with boundary. So 2-dimensional manifold looks like that. So in this case, our S1 is cobordant to empty set. So in this case, we say this manifold is null cobordant. So depending on literatures, sometimes we call this W filling of this space. So when you have n-dimensional manifold M, then we may ask that is there a filling of this manifold M? Is there a null cobordism of this manifold M? So picture looks like this. So there exists W n plus 1-dimensional manifold, and such that boundary of W is our manifold M. So by the Thom's classical work, so by beautiful theory of algebraic topology, so theorem by Thom. So if our manifold M is null cobordant, then we may have this condition. So when you have manifold M, then we can think of a tangent space. So we can think of tangent space as a function from our manifold M to Grassmannian, which is a space of n-dimensional planes. So our tangent space is representing a map, looks like this. And then we have a map between 2 spaces, so we can think of homology of this Grassmannian. And when we think of the fundamental class of manifold M, then we may think of image of our fundamental class in the homology of Grassmannian. Then if our M is null cobordant, then this image is 0. So we can check, we can use this theorem to test whether a manifold is null cobordant or not. And by the classical work with by Miller or Novikov and Wall, and in this talk, when we say manifold, then let's assume this manifold is very nice. So PL smooth oriented closed manifold. So in case of the inversion of this theorem is the inversion of this statement is not trivial, but it's known that in case of smooth oriented manifold case, this inversion is true by Miller. So beautiful algebraic topology tells us the existence of this null cobordism of a manifold which is null cobordant. So okay, but when we record the previous motivation, we may ask that. So even if we can see the existence of this null cobordism, that the algebraic topology doesn't tell us how much this null cobordism is complicated, how much complicated this null cobordism is. So in 1999, Gromov asked a similar type of question to manifold. So for a null cobordant Riemannian manifold M with bounded geometry, then the minimal volume of null cobordism W is linearly bounded by the volume of manifold M. So here we will talk about that this condition, bounded geometry condition soon. So I think picture is better. So the condition is this one. We have manifold M. So let's say d-dimensional manifold M, and Riemannian manifold M. Then there exists a filling, so a null cobordism W, d+1 dimensional manifold W, such that the volume of W is linearly bounded by the volume of M. So this bounded condition is related with a scale problem. So this bounded geometry means our injectivity radius is bigger than 1, and the sectional curvature is between -1 and 1. So for example, okay, 1. So this is the meaning of bounded geometry. So this is related with a scale problem. So for example, if we didn't bound curvatures, then we can think of this example. So here is our typical S1, but we can think of S1 looks like this. S1 looks like this. So if we didn't bound a curvature, then we may have a very small disk looks like this red disk. So in this case, so this one is unfair to ask our question. So that's the reason why Gromov add this bounded geometry condition to this conjecture. Okay, and as a topologist, the reason why I like topology is that when we change some problems to in topological language, then we can have a room for us to use some combinatorics and or algebra instead of analysis. So we may rephrase this Gromov's conjecture in terms of some PL category. So our manifold M is very nice manifold, smooth oriented and PL manifold and triangulated manifold. So we may introduce topological complexity instead of geometric complexity like a volume. So when we have a manifold M, then we can think of triangulation of our manifold M. So, and we can define the topological complexity. Sometimes we call this one simplicial complexity of manifold M. So this one is the minimum number of simplices recognizing in a triangulation, recognizing this manifold M. So, and for oriented smooth manifold, for Riemannian smooth manifold, the volume of M and this topological complexity is proportional. So we may rephrase this Gromov's conjecture like this. So simplicial complexity of W is less than or equal to C times simplicial complexity of manifold M. So this one is conjecture. So here, what I need to mention is the bounded geometric condition. So of course, there is some analog of bounded geometric condition in the PL topology. So we can think of bounded geometry in PL category like this. The number of, when we think of, so we have a manifold M has triangulation. So manifold M has triangulation, looks like this. Then we can think of a vertex, and we can bound the number of simplices which meet at one vertices. So number of simplices at a vertex. So we bound this number by some given fixed number k. Then this one is bounded geometric condition in the PI category. Okay, so what Gromov conjecture is that there is the cobordism W whose complexity is linearly bounded that of boundary. So actually there is some Gromov's result with a Cheeger, which motivate this conjecture, and today we will talk about that soon. And by Chambers and Lutterer, Manning, and Weinberger, there is a huge progress on this conjecture recently. So in the same setting, for any arbitrary small epsilon, they construct a null cobordism W, which is almost linearly bounded by the volume of M. So for any arbitrary epsilon, we can think of very small polynomial, volume of M to the 1 to the epsilon. Then, and when you think of some constant, which is dependent on the dimension of manifold M, then they can construct a null cobordism W, whose volume is linearly bounded by the almost linearly bounded by the manifold M. So the key idea is like this. Roughly speaking, the idea of their theorem is like this. So okay, we want to construct the given, we have a manifold M, the dimensional manifold M, and we want to construct the smallest null cobordism W. So in order to construct this null cobordism, they embed manifold M into sphere of dimension big M, and this dimension is very, very, very huge. Then the picture looks like this. We have manifold M, and we embed our manifold M in a sphere of very, very big dimension N. Then the image of our manifold M is contractible, so we may think of a homotopy shrinking our image of manifold M to just one point. So picture looks like this. So we continuously deform the image of our manifold M in which is embedded in the sphere N. Then we homotopy like this. Okay, so we can continuously deform our image of manifold M to a single point in the sphere. Then they construct this null cobordism W from this null homotopy, and null homotopy, and of course, the size of this null cobordism is related with Lipschitz constants of this chain homotopy. So they control a kind of size of this chain, this null homotopy, and then by using that, they construct W with a nice complexity. So this idea is repeated. Oh, what we want to construct is in this left side. In order to do that, they embed this guy into a nice space here, and then by using some information in this right-hand side, and they bring that information to the left-hand side, and they construct cobordism, which is bounded by M. So this idea is also, we already seen this idea in the motivation. So when we talk about the Tom's work, then in order to check whether our manifold M is null covariant or not, we embed we map our manifold M into Grassmannian. So we embed M in, we map our manifold into some nice space, and then by using information in here, we can see some property of our manifold. So this idea is very cool, and that idea will be repeated in today's talk. And but the reason why their bound is not linear, this one is almost linear. So this one is a polynomial with very small degree. So the reason why is that so our manifold M is a arbitrary Riemannian manifold, but we embed this guy into some Euclidean sphere. So this embedding has a natural distortion. So they have this bound instead of this linear bound, which is conducted by Gromov. But so far, this bound is very nice, almost linear bound. So, so at this, so far, this bound is the best one. Okay, so this one is our motivation, and actually, Gromov's conjecture is motivated by his work with Cheeger on rho-invariant. So let's take a look at a brief history of L2 rho-invariant. So originally, the first try is from Brother-Livesey. So Brother-Livesey introduced their invariant to classify free involution on the sphere, and Atiyah independently introduced their invariant to show that different length spaces are not covariant. And Hertzberg also introduced his invariant independently to study involution on manifold. And Hertzberg recognized that the Brother-Livesey invariant, Atiyah invariant, and Hertzberg invariant are all related. So Atiyah-Singer's work on generalization of Atiyah-Singer index theorem to manifold with boundary, they introduced Atiyah-Singer rho-invariant to generalize Atiyah-Singer index theorem. And Cheeger-Gromov introduced L2 analog of rho-invariant for Riemannian manifold with infinite pi 1. Oh, and from Brother-Livesey to Atiyah-Singer, so in this, from Brother-Livesey to Atiyah-Singer, our rho-invariant has some topological description in case of finite fundamental group. So, but Cheeger and Gromov generalized the rho-invariant to Riemannian manifold with infinite pi 1. And in Cheeger and Gromov's work, the key theorem they used is this inequality. So of course, we will look at some definition of rho-invariant soon, but the key idea is like this. We have manifold, Riemannian manifold M, and this rho-invariant, when they define L2 rho-invariant, they use the given Riemannian metric. So this one is defined in very analytical way, but they show that there exists bound, which is purely this bound depends on a pure topological type of manifold M. So, and when they define this L2 rho-invariant, they use some cobordism things. We will see that soon. So, but this inequality motivates Gromov's conjecture. Okay, so even if this one is analytically defined, there is purely topological bound like this. So people was wondering whether if there exists a topological definition of L2 rho-invariant. So in 2003, Cheeger and Weinberger introduced a topological definition of rho-invariant, and by using that, they show certain structural sets are infinite. So this set is this structural sets here means that a set of manifolds. For a given manifold, we can think of a set of other manifolds, which is homotopic equivalent to that manifold, but not homomorphic to that manifold. So by using rho-invariants, they show that this structure set is infinite. And so our rho-invariant has very key information between the homotopy type and homomorphism type informations. And our rho-invariant is very useful in knot theory, in Kaplan or Teichner or Zetuncha's work, and rho-invariant is also important in K-theory, in Piaget and Six's work. So
can I ask a question?
Yes.
In the articles that you cited above, these we have in these articles the definition of rho-invariants are the same, or there are some slight changes.
There is the Atiyah-Singer and Atiyah-Singer's rho-invariant. They have rho-invariants, but depending on literature, they are slightly different. But the main philosophy to define that type of rho-invariant is very similar. Okay, thank you for your question. Yeah, and feel free to ask me question in the talk. Okay, now, so let's take a look at the topological definition of rho-invariant. Okay, for cross-oriented 4K-1 manifold M and a representation of pi 1 of M into to any group, a arbitrary group G. So this one is the given information. And let's suppose that we have a null cobordism W, whose boundary is some copies of our manifold M. And we have a group gamma and a monomorphismal representation of from group G to gamma, and representation of pi 1 of W to gamma, which makes this diagram commute. So, and then we define rho-invariant as signature defect. So this one is L2 signature, this one is usual signature. So this one minus this, and we divide it by the number of manifold M in the boundary. So I think a picture is better. So let me draw a picture. Okay, so the given information is like this. We have manifold M, so 4K-1 manifold, and and when we have a representation of pi 1, then we may have a map from manifold M to classifying space of group G, so KG1. So KG1. So briefly, let's just say this one BG. So BG is the classifying space of group G. Then this representation in this is I map of manifolds from M to classifying space BG. So when you have this given information, let's assume that we have this picture. So some copies of manifold M are copies of manifold M, and of course we have map to BG, and let's assume that we have some cobordism null cobordism W for K manifold W. And also we assume that we can embed group G into gamma, so that induces the map of classifying space BG to be gamma. And if we can extend this map from M, from this map M to this gamma to this null cobordism W, So let's assume that we have this nice picture when given this provide for this given information. Then we define rho-invariant as 1 divided by R. So this one is just averaging the number of copies of manifold M and the signature defect. So this one is the usual signature of W, and this one is called L2 signature. So L2 analog of usual signature. So let me briefly recall what it is. Okay, so we have this manifold W, and this one is cross-oriented manifold. So when we think of coproduct of co-cycles in cohomology, then that gives us a symmetric bilinear form. So in the middle dimensional cohomology, but we are assuming the oriented manifold. So by using Poincare duality, we can think of just homology. Then the coproduct gives us a quadratic symmetric bilinear form. Looks like that. So we can think of a matrix representing this quadratic form, and so that we can define signature of W, this W, as the signature of that matrix. So this one is the usual signature. And this one, L2 signature, is a little bit different, but this one is also one of very important invariant of manifold. So when you have manifold W, then we may think of universal cover of our W. So for some reason, sometimes directly studying manifold is harder than studying the universal covering. So we want to extract some information of W by using universal cover. So we can think of universal cover of W, and so we may ask that, can we have a signature of universal covering of W? But there is some problem. Our manifold W and M and W, they are closed manifold, compact manifold. So M is closed, but our W is compact manifold. So both are compact manifold. So when we think of the rank of homology, then that is finite. So we can define the signatures. But universal covering may or may not be compact. So if our universal covering is non-compact, then we cannot define this signature of universal covering. So we need a special dimension for to detect a size, a kind of size of infinite dimensional space. So to do that, we use this representation. So by using this extension of phi bar, this map, by using phi bar, we can think of coefficients of group von Neumann algebra. So yeah, this one is some group von Neumann algebra related with this group gamma. So and by using L2 theory. So when you think of when you think of homology of the universal cover of W with this local coefficient, then we can use, there is a room for us to use L2 dimension theory so that we can detect a kind of size of infinite dimension space. So by using that, we can define L2 analog of signature. So this one is that invariant. So okay, so there are many informations, but the key point is that we define this invariant by using null cobordism of W. So and this signature and this L2 signature, these two guys are bounded by the complexity of this null cobordism W. So if we want to bound this quantity, that problem turns out to bound the complexity of this null cobordism.
Sorry. Here we mean that this is invariant. It means that if we take another cobordism M, we'll get the same number. Yes.
Yes, right. So, so of course, when we see the definition, that we need to think of the well-defined list. So, of course, there are just a minute. Okay. So the existence of this W is from some cobordism theory, and the well-definedness of this invariant is from Novikov additivity. So the key idea is not that. Key idea is like this. So let's assume that we have this picture looks like this. We have we have another picture with, so this one is W prime. Then of course this W prime may have different copies of M, so R prime copies of M. Then in this case, we can think of, but this number is not important because we average it. When we define rho-invariant, we averaging the number of copies. So we may assume that they have the same number of M as a boundary. Then we can, now when you have these two ordinals and we can glue them together, and it's known that 4K minus 1 manifold, this 4K manifold, the signature of 4K manifold is 0. So that gives us the well-definedness of this definition. So,
and do we use that our geometry is bounded?
Sorry?
Do we use that our geometry is bounded in the sense that the curvature?
So in this, so this one is a topological definition. So this one is generalization of Cheeger-Gromov to rho-invariant. So this one is topological manifold. So we didn't use geometry.
Thank you.
Mm-hmm. Oh yeah, thank you for your question. Oh, so regarding that question, I have to mention one more thing here in the motivation. Let me see. Right. So we talk about the bounded geometry to make this conjecture fair. Yeah, but if in case of high-dimensional case, this behavior is not general thing. So we don't know whether this one is true in case of unbounded geometry. So there is still in case of bounded geometry, there is a very nice progress from them. Yeah, but in case of unbounded geometry, so this Gromov's conjecture is still mysterious. Yeah. So we are talking about the topological definition of it. So in this setting, our manifold is, we can think of this manifold is unbounded geometry, so without bounded geometry condition. So this one is just about the topological manifold. Yeah, thank you for your question. Okay, excuse me. Okay, good. Okay, so we know. So the point is that, so what you want to do is detect the size of this null cobordism and satisfying these conditions. By Jackson Cha in 2016, he showed that the linear bound of L2 rho-invariants. So this inequality is special because when Cheeger and Gromov obtain this inequality, to obtain this bound, they define this one very analytic way, and they know that this bound is dependent on a purely topological type, but this just inequality is optimal result. So this quantity is linearly bounded by a manifold M. So when we record the definition of rho-invariant, then we define this one is bounded by the complexity of W. So, and what Cha showed that is that the size of null cobordism W can be linearly bounded by the complexity of manifold M. So, and furthermore, this inequality is universal bound. Universal means for any arbitrary representation, this inequality is true. So, okay, so we will take a look. We will see the key idea of his theorem. So this theorem, the proof of this one contains two parts. So first one is algebra part and some geometric, excuse me, some geometric construction part. And recently I had a slightly better bound. For any arbitrary three-manifold case, I have a still linear bound and with a small coefficient. And for some special three-manifold case, I have much nicer coefficient. And I improved some parts, something in algebraic process. And now algebraic process. So now let's talk about that. So the key idea is using the Bamslag-Dyer-Haller's acyclic functor. So let's see this picture. So this one is the given information. We have manifold M and representation of pi 1 to some group G. And by Kahn and Thurston's and Bamslag-Dyer-Haller's independently, they show that we can embed any group into acyclic group. So this group is acyclic. So that means the homology of this group is all zero except the zero dimension. So, and furthermore, Baumschlag-Dyer-Haller's construct a functor embedding a group into some acyclic container. So for this given information, we can take the functor to obtain this diagram. And so this one is 3 manifold, this one is 4 manifold. So we can think, so in the previous motivation and the recent progress on Gromov's conjecture, the key idea is that we embed our manifold into a nicer space or nicer group. So that idea is repeated again here. So we embed we have a map. We embed our pi1 into some acyclic group. So when we see the image of fundamental class of manifold M in the homology of this group, then that is 0. So that means when you think of pushboard of our fundamental class in the homology of this acyclic container, then since this group is acyclic, so homology is 0, just trivial. So this one is just trivial. So that means we may have one-dimensional higher chain U in certain chain of this group, then such that the boundary of U is the image of our manifold M. Then construct this W by using the given manifold M and this full chain U. So, and we obtain this full chain U in the homology of this group. So this full chain U is dependent on this one depends on only our manifold M in this acyclic functor. So this W is independent of the given representation. So we may, if we are able to detect the size of this W, then we can have the universal bound for rho-invariants. So this is correct. This three step is algebra part, and this part is some geometric topological geometric topological process, and but the reason why his argument works for only low-dimensional case is that when he computes this full chain U, he needed to use computer to solve very big system of linear equations. So about 1,000 linear equations in 3,000 variables. So very huge, excuse me, a very huge system of linear equations. So yeah, so that's the one reason why he didn't get the linear bound for high dimensional manifold. And one more obstruction is in the geometric topological process. When he construct this W from the U and M, and he removes some certain singularities from these conditions. Omega 1 and omega 2 and omega 3 is 0. These guys are the oriented Buddhism groups. So that means 1 manifold, 2 manifolds, any 3 manifolds are null cobordism. So so we just talk about oriented manifold case. So, but this one is not true for high-dimensional manifold case. So yeah. So that's the reason why this argument works for only low-dimensional case. And today, our main result is to obtain linear inequality for high-dimensional manifold case. And one thing I want to mention is that when he found out this U, he needed to solve very big system of linear equations. And but in my previous result, I solved that problem without any computer by employing some combinatorial concepts of polyhedra. So, and that idea is also used for this joint work with Shmuel Weinberger. So let's talk about that soon. Okay, so here is our main result. Excuse me. Okay, here, what time is it? Okay, so here is our main result. So let our M is PI for K minus 1 manifold, then our rho-invariant is linearly bounded by the topological complexity, so simplicial complexity of manifold M for any faithful representation. So we have a linear bound, this nice linear bound, but we need to put some condition on this representation phi that this phi should be a faithful representation. So this one is injective homomorphism of groups. Okay, so to show this theorem, we need this theorem, but I think the picture is better. So let me sketch. Let me draw a picture. So we have manifold M, looks like that, and we have a phi to the corresponding group BG. So in order to obtain rho-invariants, we need a null cobordisms. But there is very nice observation in Zetun Cha's paper that if we have a cobordism from M to M prime, another manifold M prime, and let me see, M prime, and we embed group B gamma M prime. If we are able to extend this map phi to this cobordism W, this W, to this gamma, so that this diagram commutes, and so we have this extension phi bar, and when we think of the restriction of phi bar to this M prime, if our phi bar is trivial, our phi bar restriction to M prime is trivial if we have this picture instead of null cobordism. So this one is just cobordism, not null cobordism. So this picture is easier than the picture in the original definition. So if we have just cobordism satisfying this condition, then we may obtain our rho-invariant from this cobordism instead of null cobordism. So we can avoid the difficult part of the cobordism part. So the reason why we can use this is that our rho-invariant is defined on manifold M and the representation phi. So here we have the given information, but at the bottom we have manifold M prime endowed with a trivial map. And when we record the definition of rho-invariant, then And if we use just trivial representation, then this L2 signature is equal to just signature. So our rho invariant of m prime is just 0, and we define, and the signature is when we glue two manifolds. When we glue two manifolds, then we can just add the signatures. So when you have manifold M endowed with trivial representation, then we may bring any cobordism looks like that, and we can extend this trivial map to this cobordism. So this part doesn't affect to our invariant. So that's the reason why we can use just this cobordism instead of the cobordism. So so what this theorem tells us is that we can construct this type of manifold W. So with the complexity of this cobordism is linearly bounded by manifold M, so we may have this inequality. Okay, so in this picture, yes, it looks trivial because this one looks like M cross I. So so the complexity of this one should be linearly bounded by M, but the process is not that trivial. So in order to obtain this cobordism, we need to use a hyperbolization method. So let me explain the key idea of hyperbolization. So hyperbolization is, the idea of hyperbolization is simple. When you have a manifold M, then triangulated manifold. So we have a simplex in a triangulation, and we want to obtain a hyperbolic manifold which is related with the given manifold M. So we will replace a simplex with a hyperbolized simplex. So like this picture. So this one is our manifold M and a triangulation. And this one is a hyperbolized simplex, and we replace this simplex with hyperbolized simplex, then we can obtain hyperbolization of manifold M. So picture looks like that. So this one is our manifold M, and we have a triangulation. This looks like that. And hyperbolized simplex is some geometric shape which is a with a negative curvature. Looks like this. Then we replace each simplex with this one. Then the hyperbolization of manifold M looks like this. Looks like this. Okay. So the good thing of this hyperbolization is this one. So when we think of generator of our pi 1 of M, then since this generator in hyperbolization of manifold M, then because we have some pillar or column looks like this. So this generator will be non-trivial in the hyperbolization of manifold M. So by using this idea, we may obtain the desired cobordism. Okay, so I think picture is better. So let me draw a picture. Okay, so we can have so the given information is our manifold M. Excuse me. And we have a triangulation of manifold M. Then we can think of the suspension of our manifold M. And then we can triangulate it. This suspension looks like this. Then we have these two cone points here. And then we subdivide each simplex. Now we can use the barycentric subdivision, looks like this. And then we do the hyperbolization. Then we replace each simplex with hyperbolized simplex. So the picture looks like this. Okay, now when we remove the singularity of these two components, then components looks like that, and we may have two copies of manifold M. Looks like this. Okay, then because of this hyperbolization, when we think, okay, let's call this cobordism is W. Then when we think of the pi1 map to W, then this one is this embedding, and this embedding gives us pi1 injective map. This one is pi1 injective map. So, okay, but because there are so many hyperbolized simplices, so any generator of any generator of M in the top M cannot is not homotopic to a generator in the bottom manifold M. So if when we think of the pi1 quotient, pi1 of W and quotient by the bottom thing, pi1 of M prime, then the bottom map will be pi1 trivial. So this one is a desired cobordism. So we may obtain the rho-invariant of manifold M by using this cobordism. And this hyperbolized, the size of this hyperbolized simplex depends on only the dimension of manifold M. So we can linearly bound the rho-invariants of manifold M. So this one works for any 4k-1 manifold. But in this case, we need to put some condition that our representation phi is faithful. Okay, so now we have a similar result on the another different type of rho-invariant called Atiyah-Singer classical rho-invariant. So and we have a similar linear inequality like this, and the proof of this theorem contains a combinatorial concept of polyhedra. So let's talk about that. Okay, so the definition of Atiyah-Singer's classical rho-invariant. So they define rho-invariant as a certain element in the complex representation ring, and when we think of the character of that representation, then we can have a quantity. So we want to bound that quantity. So, but in this case, rho-invariant is different with Cheeger-Gromov rho-invariant. The picture looks like this. So the given information is similar. We have manifold M, but in this case, 2k-1. In the Cheeger-Gromov manifold, rho-invariant is about 4k-1, but this one is, we can define this in rho-invariant for any other dimensional manifold. And we have alpha representation to some group G, but in this case, our group G is finite. So that's the reason why this is called classical rho-invariant. And the picture looks like this. When we have some copies of M, R copies of manifold M, and go to map to classify as BG, and let's assume that we have a null Bodism. so null cobordism W looks like this. But in this case, we didn't embed group G into larger group or acyclic container, something like that. So the condition we need is that we should be able to extend our alpha to this cobordism W. So if we can extend our alpha to this cobordism, then we can define this rho-invariant as a signature of this signature of W tilde. So this one is G cover of W. So the idea is that we can define this rho-invariant by using this null cobordism. So if we want to bound this quantity, we need to bound the complexity of this W. And in this definition, they use the G cover of W tilde. So we need the we need to multiply by the order of group G. So, but if we ignore this one, then yeah, this one is also a linear inequality. So so our question is this one. Then how can we construct this null cobordism W with very nice complexity? One thing I need to mention is that, and in our theorem, we put more condition on group G. G is finite and abelian. So very nice group. Okay, now to construct that null cobordism W, we employ a concept, a combinatorial concept of polyhedra. So because in this case we cannot use, we didn't use acyclic functor argument, so we need to replace that with finite abelian groups. So, and by modeling some abstract simplex in the word complex as a combinatorial simplex. Yeah, so I think so. Okay, so let's see this picture. So here we are mapping our manifold M into classifying space BG, and G is very nice group, finite and abelian. Then when you have this map, then this alpha induces a nice map of some certain chain complexes. So let's say, so that alpha. So we have manifold M, and we have triangulation, looks like this. So we can think of the chain complex of this manifold M, and the representation alpha induces a chain map from manifold M to a more chain complex. So this chain complex of the classifying space of group G. So so this one is a certain nice chain complex induces from some simplicial set theory. Simplicial set theory, and the way we model a simplex in this complex by using a combinatorial polyhedra is like this. So we have a simplex in this triangulation, and then we map this guy into an abstract simplex, and which is labeled by group element to each edges. So for example, A, B looks like this. So this one is two-dimensional picture. So to determine, in order to determine the two-dimensional simplex, these two group elements in two edges is enough. So because these two guys gives us the group element, which is assigned to this other edge. So this one is A times B. So when we follow this direction, then we have this. When we follow, when we think of a loop of this simplex, then that should be trivial. That's the condition we need in order to model a simplex in abstract simplex in this more complex. So and our group G is abelian, so we can say we can model looks like this. Okay, so so when you have this long this chain in the more complex, then when we compute the differential of this more complex, then we can check that this one is actually a cycle. So the boundary of this chain is 0. We can compute that. But by using picture, we can easily model this chain in a nice picture. So when we think of this, excuse me, when we have a polyhedra and we assign a group element to each edge, such that any loop of this polyhedra representing the trivial element. So in this picture, when we think of the starting point, then when we go to this clockwise direction, then this loop representing A times and then B are so B times C times, and in this case we have the opposite direction. So in this case we multiply by the inverse of C, so C bar and A bar and D bar and B and D bar. So since our group is abelian, so cancelled out. So this one is just in. So we can see that the chain which is modeled by this picture is cycle. And when you think of the subdivision of this polyhedra, then we can have picture looks like this, and this one is a model of this chain and this cycle in more complex. Okay, and so what we want to do is to construct these null cobordisms of some copies of manifold M. But here we use the nice observation again. So when we have cobordism instead of null cobordism, looks like this. So this is M prime, and such that if our alpha bar, a restriction of alpha bar to M prime is just trivial, then we can use this cobordism to obtain this rho-invariant. So when we interpret this idea in the more complex, then what we want to have is this picture. So we have A, B, and B, A. So this one is a part of manifold M, and we want to copy this one. We want to have several copies, looks like this. And what we want to obtain is null homotopy in this more chain complex. So what you want to obtain is, so okay, so, and maybe we may group this one to here, then we can think of some copies of manifold M. Copies of manifold M looks like this, and looks like that, and we have similar same polyhedra with a directed graph looks like this. But in this case, what you want is each edge is labeled by trivial group elements. So if, and okay, so let's assume that this part is our manifold M, this part is our manifold M, this part is manifold M. And if we have a picture looks like this, then we may, this one is our one-dimensional higher chain U, whose boundary is some copies of our manifold M and other copies of one manifold M, but we may extend the given representation to this homotopy, such that at the bottom, the restriction of that map to bottom is just trivial, because we labeling each edge is just trivial group element E. So in order to do that, we think of similar combinatorial concepts like this. So this one, this polyhedra are labeled with group element is the previous picture, this one. So we know that this one is a cycle. And we, by using this information, we may assign group elements to each vertex. So if we assign group element E here, then when you follow this edge, then we do the right multiplication. So we may obtain A. So for following this edge, then we have AB, ABC, and for this direction is opposite direction of this directed graph. So we may have we assign AB to this point, so and so on. So we can assign group element to each vertex, and this picture is actually one-dimensional higher chain. So this picture means models one-dimensional higher chain. So looks like this right picture. So we can think of, so this one, this polyhedron is this given polyhedron, and excuse me, and we can think of one-dimensional higher chain. Some cylinder of this polyhedron looks like this, and this E means we add edge from bottom to top, and when we go from bottom to top, then we assign this group element E. And this group element A means this edge, we assigned A to this edge. So AB, then we assign AB here, ABC, then we assign to these edges, and so on. The good thing of this model is that if we assign group elements looks like that, then we can assign just a trivial group element to each edge at the bottom. So this two-dimensional picture actually means these three-dimensional pictures. So now the question we have is that so this one is our manifold M, and we want to find out some R copies of M, R copies of manifold M. So okay, so copies looks like that, and then when we glue them together, then what you want to have is the same copies, but with the trivial group element. So let's construct this one. So the idea is that, so okay, so let's return to this picture. Then this one was a cycle in the chain complex. So cycle means if this one, when considering orientation, this one is +A, this one is -A, so we can cancel them out. So pairing in these guys. But in this picture, we cannot cancel these two guys out. Because in this case, we have labeling at each vertices. So because they have different group elements at the vertices, so we cannot glue them together. So like this picture. So what you want to do is to find out R copies of this guy to have, in order to have the same group element at edges and the same group element at the vertices. So to obtain that things, we introduced the concept of cover of polyhedra. So when you have this polyhedra and we have very nice group, finite abelian group. So let's assume that the order of our group is just 5. Then we first let's just think of this picture. Then first, let's think of just 5 copies of our polyhedron. Then we glue -A and +A here and here, and then here, looks like that. Then since our order of our group is 5, so starting from here to here, then this part, all the same, 5 times, repeated 5 times. So the group element at this vertex and group element of this vertex are the same. So similarly, this vertex and this vertex are the same. So we may glue this part and this part together when we think of one-dimensional higher pictures. So our manifold. So in this example, our manifold M has 4 pairs of edges. So A, B, C, D. So we do this process for each edges, each pair. So for this, from this process, we can cancel out all A, and then we think of 5 copies of this one, and in order to glue B guys, -B plus B, and -B plus B, and so on. So here, and these green guys, and these purple guys, and these brown guys. So, and we repeat this for every pair. Then we may obtain very many copies of manifold M, and that represent a one-dimensional higher chain to the same copies of manifold M with just trivial group element E. So, and when you recall the definition of rho-invariants, and the number of copies of M, it doesn't matter because we average that by the number of copies. So this process doesn't increase the complexity of our cobordism. So, and the size of this cylinder is dependent on the dimension, so we can obtain this linear bound. And this multiple constant of order of group G is related with the induced, since we use signature of induced G cover instead of the universal covering in case of Cheeger-Gromov rho-invariants. Okay, so excuse me. So by using the linear inequalities, excuse me, we can have a concrete examples in the complexity theory of manifolds. The first example is in the typical length space in 3 dimensions. So this delta is the topological complexity of manifolds, the simplicial complexity of manifolds, and this complexity, the definition of this complexity is very natural. The smallest number of simplices to recognize this manifold. But however, even if the classification of 3 manifolds is well known, the classifying manifold with finite number of simplices is a hard problem. So McPhee and Jacob-Rubinstein and conjectured the simplicial complexity of these length space and length spaces, and one is n-3, and they show that this upper bound by some concrete construction, but this lower bound was still hard problems. But Cha and Lackenby and Purcell, they independently show that this complexity of the length space is linearly bounded by n-3. And in Cha's work, he used the universal bound for rho-invariant of length spaces to obtain this lower inequality. And in the low dimensional manifold case, the complexity theory is still mysterious and difficult. So there were a few examples in high dimensional case. So by using our result, we can obtain an analogous theorem about the simplicial complexity of high dimensional length spaces. So by using some specific construction, the joint construction, we can obtain this upper bound. And by using our linear bound for rho-invariants, we can obtain this lower bound. So this one is a generalization of the conjecture of McPhee and Jacob-Rubinstein. And another application of our result is about the homotopy length spaces. So depending on literatures, sometimes we call homotopy length spaces fake length spaces. And this one is a orbit space of free actions of finite cyclic group on a sphere. So, and our rho-invariant is very useful invariant to classify homotopy length spaces, and we can obtain the rho-invariants as we can have the bound of our rho-invariants as a function of simplicial complexity of a manifold. So by using that, we can count the number of a structure sets. So for example, this first theorem is that when we think of set, we can think of homotopy class. So this one is this one is H cobordism class, and such that our manifold N is homotopy equivalent to given length space. This one's N. And the given length space is d-dimensional length spaces with pi 1 is Gn, and simplicial complexity of our manifold M is bounded by some number D, then the number of H cobordism class of this guy is linearly bounded by V to the n-1 divided by 2 plus some delta term. So this delta term is 1 or 0, so depending on dimension. So this one tells us some concrete example on the complexity theory about homotopy length spaces. And so this one is the number of H cobordism class, but it's more natural to ask similar question to the homomorphism class. So this second theorem tells us when you think of manifold M, homotopy length space M, but in this case we need to add bounded geometric condition, and then M is homotopy length spaces, length space with pi 1 is Gm, and the volume of our M is bounded by V. So recall that volume of M is proportional to the simplicial complexity of manifold M. So we can also use our inequality to count the number of these sets. Then number of homotopy length spaces less than this volume with this fundamental class is linearly bounded by V to the n minus the n plus delta. And delta is the same delta here, so the 0 or 1 depending on the dimension. And this big N is related with our fundamental group, and D of N is the number of divisor of N. So of course there are more ingredients to obtain these two theorems, but our inequality for rho-invariants plays a key role to obtain these examples in the complexity theory of high dimensional manifold. Okay, so this one is what I prepared today. And for further work, we may ask some question like this. So our inequality for high dimensional manifold, our linear bound for high dimensional manifold is not universal. So we may ask that, can we obtain universal linear bounds for high dimensional manifold? So that can be a very interesting question to me, and I have some projects with Jaechun Cha to solve that problem, that question. And one other question we can have is that can we generalize these inequalities for a generalized manifold? So width spaces is a generalized manifold with some singularities. So, and in this, for that generalized manifold, we may define signatures, rho-invariants. So we may ask whether if we can obtain the linear bounds for this type of generalized manifold with some singularities. So this one will be my future project. Okay, so this is all I prepared, and thank you for listening.
Okay, thank you very much. Are there any questions from the audience?
Can I ask a very random general question? So, yeah, so I think at some point you said you had this when you're giving your construction of like a higher boundary of this like cycle. Do you know what are like possible like higher boundaries? Because I think if I recall correctly, there's like a particular construction. So I was wondering if there's some like space of like higher boundaries for a particular cycle.
Let me see. So boundary of sorry. So can you say?
So I guess in the next slide you had like a particular tower giving a higher boundary. So I was wondering what is the like what are the other possible constructions of a higher boundary, basically.
Right. So so this one is the schematic picture and easy example in the 2 dimensions.
Yeah.
So high dimensional simplicities, then there are more there is a tricky part we need to care about. So one example is like this. So the condition we need is that when we think of any loop, then this loop is representing this loop should represent a group relation. So when we think of the high dimensional case, then when we copy these guys, bunch of these copies, and we glue them together, then there should be non-trivial loop in topologically non-trivial loop. But we need to check whether this guy is this loop representing group relation or not. But we can solve that problem because this one is a covering of polyhedra. So this we can think of the image of this loop on the bottom. So we have a covering space, and we have a loop here, and then we map this guy into the bottom, and then so this one is a loop. So this loop represents a group relation. So we can bring this information. We can take this information to the top again, so that we can see this loop represents a group relation. So so we need to check that part. We need to check that part in high dimensional case.
Okay. Thank you.
Thank you for your question.
Any more questions? Doesn't seem to be the case, so I will stop the recording for now and